Hello everyone. Today we will talk about what is known as Lipschitz continuity. Okay, so let me first write down the definition of Lipschitz continuity. We again talk about a function f from j to r. We have a function f defined on some set j, which is subset of r to r. Okay, so we say that this function is Lipschitz continuous. We say that f is Lipschitz or Lipschitz continuous on J if there exists L greater than 0, there exists some positive number L such that mod fx minus fy is less than or equal to L times mod x minus y for all xy in J. Okay, so Lipschitz continuity says that we have a function f which satisfies this condition for all points in the domain. Okay, mod fx minus mod fy should be less than or equal to L times mod x minus y. Now first obvious question, Lipschitz continuity and continuity. Which of them is a stronger condition? Okay, what do I mean by that? Means if Lipschitz continuity implies continuity, then we will say that Lipschitz continuity is a stronger condition. Okay, so let us see if that happens. So we will try to examine if Lipschitz continuity implies usual continuity. Okay, because reverse way, okay, this also we'll check, but first let us check this way. So what would it mean? It would mean that suppose I have been given that a function is Lipschitz continuous or a function satisfies this Lipschitz condition. So f is a function which is defined from j to r and f is such that mod fx minus mod fy is less than or equal to L into mod x minus y for every xy in G. And we have to check whether it is continuous. So our claim is f is continuous. F is continuous means what? Given epsilon greater than 0, we should be able to find delta such that mod x minus y less than delta implies mod fx minus fy less than epsilon. So let us try. So I want to make fx minus fy less than epsilon, and I know fx minus fy in modulus is already less than L into mod x minus y. So if I can make L into mod x minus y strictly less than epsilon, then my job will be done. That is, if I make mod x minus y less than epsilon by L, then my job will be done. So basically what? So it says, so this is of course our background calculation. So given epsilon greater than 0, take delta as epsilon upon L. Then what will happen? We will have mod fx minus mod fy less than or equal to L into mod x minus y by Lipschitz condition. And because we have chosen delta as less than, okay, not equal to, delta is less than epsilon by L, I will write this as less than epsilon upon L, which is equal to epsilon. So if, of course, mod x minus y is less than delta, then fx minus fy becomes less than epsilon. Hence, we have proved that Lipschitz continuity implies continuity. Okay. But in general, does continuity imply Lipschitz continuity? So suppose I have a function f which is defined on r to r with fx as x square. Then mod fx minus mod fa, we want to check whether it is less than or equal to L times mod x minus a. Okay, so basically we want to check whether mod fx minus mod fa upon mod x minus a, can it always be less than L? In this particular case, it will be mod of x square minus a square divided by x minus a, which is mod x minus a into mod x plus a divided by mod x minus a, which is equal to mod x plus a. Okay, and because my x takes uh, any value in the domain, it is not possible to find an upper bound for this because x is any real number, a is any real number. Okay, so it is not possible to find an upper bound for x plus a. Hence, we can say that fx equal to x square, if I define f from R to R, is not Lipschitz continuous. But we know that it is a continuous function. Okay, so continuity does not imply Lipschitz continuity. So Lipschitz continuity is a stronger function. In fact, we have already studied a few things in our 11th, 12th. What is differentiability? How do you compute derivative? Derivative by first principles, when we try to compute, it is something like f of x plus h, of course, limit h going to 0, f of x plus h minus fx divided by h, correct? This is how you define derivative by first principles. So, this is basically similar to mod of fx minus fy divided by mod x minus y. Okay, so if the first derivative of a function is always bounded, then the function will be Lipschitz continuous. Can you see that? Because this will be like a derivative. So if this is bounded and it has this bound L, then the function becomes Lipschitz continuous. Okay, so this is Lipschitz continuity. We you can see that it is in some sense related to uniform continuity. Okay, because like uniform continuity, Lipschitz continuity is also defined for general xy in the domain. Okay, it is not defined at a particular point A. Okay, now we have to finally go to what is known as intermediate value theorem. But before that, we need to study few more local properties of continuous functions, which we will try to study now. And Lipschitz continuity is kind of, a precursor to that. So what is Lipschitz continuity telling me is that value of fx minus fa is within a certain bounds of the neighborhood size of x minus a. Correct. So basically, if I bring x close enough to a, then my fx will be close enough in some sense to fa. Okay. So a natural extension of this idea is, let me draw a picture. So if I have a continuous function, okay, let me suppose this is my continuous function. Now, if my function is say positive at a particular point, for example, I consider this point. At this point, the function is positive. If the function is positive at a certain point, can I say that at least within some neighborhood, it stays positive? Okay. At this point, it seems very obvious. But when I am very close to the x-axis, for example, if I am here, okay, so I'm considering this function value. So this function value corresponds to this. So I can still find, if I magnify, I can still find a very small neighborhood here such that the function stays positive within that neighborhood. Correct? On the other hand, if a function takes negative value, let us say here, I can still find a small neighborhood in which the function always takes negative values. That is actually one of the nice properties of continuous functions. In fact, that is what continuity is, that there are no sudden jumps in the values. If a value is positive at a certain point, at least in the small neighborhood, it stays positive. If a value is negative at a certain point, at least in some neighborhood, it stays negative. Okay, so we will try to show this. Okay, So how do I do that? So what my claim is, so suppose I have a function f which is continuous from j to r. First let us formulate the problem and then we'll try to discuss it. So f is a function defined from j to r and f is continuous. Okay, this is given to me. F is continuous. Okay, suppose a and b are points from the domain such that points from the domain that is j such that fa is positive and fb is negative, and our claim is there exists delta a delta b greater than 0 such that for all x belonging to n delta a of a, fx is positive, and for all x belonging to n delta b, fx is negative. This is my claim. Okay, so we suppose consider a first. Okay, so we are talking of continuity at x not equal to a. So I know that for every epsilon greater than 0 there exists delta greater than 0 such that fx minus fa is less than delta mod fx minus fa is less than epsilon for every x in delta neighborhood of a. What I want is, my job is to find delta a such that if x is greater than 0 if x belongs to n delta a of a. That is my job. Okay, so what I want is, I want fx greater than 0. What I know is fa is greater than 0, so we will use the same trick. So a is here. Okay, and what I know is fa is somewhere here. So if I can make sure that fx stays in this neighborhood, then my job is done. So here I can call this as fa by 2. If fa is positive, then fa by 2 is positive. Okay, so if I can make sure that fx stays in this neighborhood, so fx should be belonging to fa by 2 and some upper bound. Okay, that is fx should be greater than fa by 2. If I can do that, then my job is done. Okay, how can I do that? How can I make sure that fx stays larger than fa by 2? That's how I will choose my epsilon, right? So I want when when fa is positive, I want fa minus epsilon to be larger than, or I can write equal to, fa by 2. fa by 2. So what is my choice of epsilon? My epsilon is actually fa by 2. Okay, so if we take epsilon equal to fa by 2, then there exists delta greater than 0 such that mod of fx minus mod of fa is less than epsilon, that is fx belongs to the interval fa minus fa by 2 to fa plus fa by 2, that is fx belongs to the interval fa by 2 divided into comma 3fa by 2, and this implies fx is always positive. Okay, so this delta is actually the required delta, so this delta does the job of delta a. Okay, similarly for negative, what will I write? So for negative, what will I write? I have b here and this is suppose fb, then I'll make sure that fb by 2 is actually fb plus epsilon. Okay, so we choose epsilon such that fb plus epsilon is fb by 2. This happens because fb is negative. Okay, that is epsilon equal to fb by 2 minus fb. So epsilon equal to mod of fb by 2. In fact, I can write a general epsilon as mod of f at that point by 2, because earlier also epsilon was fa by 2, which is same as mod of fa by 2. Now with this epsilon, so given epsilon equal to mod of fb by 2, there exists delta greater than 0 such that mod of fx minus fb is less than epsilon for every mod x minus x, such that x minus b is less than delta. So this means fx belongs to this. So fx is in the interval. So I will also have fb minus epsilon. So minus epsilon means fb plus fb by 2. Okay, so 3fb by 2 comma fb by 2. Fx is in this interval, which implies fx is always negative for this delta. This delta can be taken as now delta b. Okay, so this says that if a function is positive at some point, then we can always construct a neighborhood where it is positive throughout a neighborhood. And if a function is negative at some point, we can always construct a neighborhood where it is negative throughout. Okay. This leads to the concept of what is known as local boundedness. Okay. So what is local boundedness? Let me define. So local boundedness of a continuous function. Okay. So suppose I have a function f from j to r such that f is continuous at a, then f is locally bounded at a. Okay, f is locally bounded at a. What does it mean? It means that there exists delta greater than 0 and another number m greater than 0, such that for every x in a minus delta to a plus delta, of course in the domain, mod fx is less than m. Okay, because in that neighborhood we know that the values do not go beyond epsilon neighborhood of fa, hence the values stay within certain bounds. Okay, so basically it will be in the case of real value functions, it will be actually something like maximum of fx fa minus epsilon and fa plus epsilon. Okay, m will be something like maximum of fa minus epsilon and fa plus epsilon, of course in the modulus. Okay, so this is local boundedness, and you can see Lipschitz continuity does something similar. Okay, it is trying to confine fx minus fa to certain multiple of x minus a. So let me, because we have time, let me take an example of a function which is Lipschitz continuous, and we saw one function which is not Lipschitz continuous, right? When we were proving that continuity doesn't imply Lipschitz continuity. So let us construct another example where the function is suppose Lipschitz continuous. So suppose I have f which is defined from interval -2 to 2 and r, and I'll take the same function fx equal to x square. Now what do I know about mod fx minus fa or mod fx minus fy upon mod x minus y in general? It will be x square minus y square divided by x minus y, which is equal to mod x plus y. And we know the largest possible value is mod x plus mod y, and largest possible value for mod x and mod y is 2. Okay, so if you take L equal to 5, let us say, then we will always have mod fx minus mod fy less than 5 times mod x minus y. Okay, so if you define the same function on a finite interval, it becomes Lipschitz continuous. Okay, in fact, um, we talked about bounded derivative, right? So if I compute derivative of fx, it is 2x, and you can see this is bounded in this interval because x is between -2 to 2. 2x is always between 4, so mod 2x is always less than 4, and we get exactly the same bound here. Okay, so this is an example of a function which is Lipschitz continuous. But does it mean that every function defined on a finite interval is Lipschitz continuous? Let us check. So if I define f from 0, 1 to r as fx equal to 1 by x, then I will have mod fx minus mod fy divided by x minus y as mod 1 by x minus mod 1 by y divided by mod x minus y, which is equal to mod x minus y, mod x y, and mod x minus y, which is equal to 1 by xy, because anyway x and y are both positive. And now we know that because my x and y are both taking values in 0, 1, I do not really have a bound on 1 by xy. So even though f is defined on a finite interval, it is not Lipschitz continuous, even though it is continuous on that interval. Okay? And conversely, so we have seen one example where f is defined on infinite interval and it is not Lipschitz continuous. We have seen one example where f is defined on finite interval and it is Lipschitz continuous. Now we have an example where f is defined on finite interval and is not Lipschitz continuous. Now next is, if I define f on an infinite interval, will it never be Lipschitz continuous? Okay, so suppose I define f from 1 to infinity to r, so this is an infinite interval, and I define fx again as 1 by x. Okay, and let me consider mod of fx minus fy divided by mod x minus y. So this is again 1 by x minus 1 by y divided by x minus y, so which is mod y minus x divided by mod xy into mod x minus y, which is equal to 1 by xy. Okay, and we know that x and y both are greater than 1. As a result, 1 by xy is always less than 1. So the function is Lipschitz continuous even though it is defined on an infinite interval. So what we are trying to say here is, whether the function is Lipschitz continuous or not does not really depend on whether the interval, the domain is finite or infinite. Okay, so we have all possible combinations here. Okay, homework is try to construct few more functions which are Lipschitz continuous, few more functions which are not Lipschitz continuous. Okay, let me stop here. Thank you.